see schematically how it works. That is not very surprising because it's mostly how you will work anyway. Right? So the first thing you do is you create a workspace, which is kind of a unit of work. I don't know, maybe think of it as what you do in your working group or your department. And within this workspace you have several experiments that you carry out. And each experiment can have multiple models and model history that we track for you. And once you have a model within an experiment that you think is good, you can just deploy it, right? And a deployed model is, by definition, a service, and from the service you can get predictions, right? And if you kind of follow the story I just laid out, then you can also read the Python code that comes with it, right? So you create a skill server, a workspace in it, then an experiment, and then with some model files, so in this case, it's model H5, it's supposed to be a Keras model, you create that. That will be under the hood imported into our platform, will be managed for you. Then you can deploy it, and the deployed model of the service can be deployed at some scale, so that does some auto-scaling for you. Alright, cool. That was just a quick introduction. We will see an example of scale in a bit. So something I wanted to briefly touch as a use case to check out is object detection, right? So the task in object detection is given an image. What do we see in this image? Can we label it quite accurately? Can we draw bounding boxes around it, right? And so we've seen quite some improvement in the last couple of years when it comes to object detection. So I don't know, has someone worked with object detection like maybe 5 to 10 years ago? was quite interesting. So we had stuff like feature engineered hard-coded features, like for face detection we used cascading Haar filters, which essentially used, I don't know, the fact that like on a black and white image, your nose is essentially a vertical white bar, and your eyebrows and your eyes are essentially a black bar horizontally, and stuff like that. So it was heuristics like that that made it work, and it did work reasonably well, right? It wasn't just extremely fast and very limited in the use cases. And today, as far as I can see, the field is pretty much dominated by deep learning approaches. So, yeah, I don't know the exact time frame, but in the beginning, people used or reused classifiers for image detection, right? So, I mean, you can define, I don't know, a classifier which distinguishes cats and dogs, or whatever, right? And of course, you can do this for object detection as well by doing a sliding window approach, right? Defining a window that slides through your image and always asks, is this a dog, is this a dog, is this a dog, essentially. And this also works quite well, but it's kind of slow, right? And so the next wave in this development was region proposal-based algorithms. So you had deep learning algorithms which kind of first, I mean, not necessarily deep learning algorithms, but algorithms who made smart proposals on where to look for stuff, followed up by essentially the same thing as I said before. So ask your classifier is something on that image. And after that, there's like the current state-of-the-art wave, maybe faster RCNN, YOLO, which stands for you only look once, or SSD, which is single-shot multi-box detection. And the advantage of those, especially the last two, is that you train one network on the whole object detection task. So YOLO in particular is just a regression task on fitting the bounded boxes and optimizing for intersection. What was it? Overlap under. I forgot the name of the metric. Intersection under overlap. I forgot. Sorry. But essentially, you look how closely your labeled bounding box fits your predicted bounding box, and you divide intersection of a union, right? So I just needed to explain it. You see how much the images overlap and divide that by the area of the union. And the closer they are, the closer you get to 1. And then you do a regression normal on that. And so YOLO uses a deep convolutional neural network to achieve that. Right. And so this quote you don't have to read, but I can urge you to read the papers by this guy Joseph Redmond. He's a really funny guy. So on version 3 of his YOLO paper, he essentially says, right, okay, now we have those detectors. What are we going to do with it? Right. Luckily, nobody works for advertising companies and so on. And he rambles on by telling you about use cases in the army and whatnot. So it's kind of a fun read. I mean, this is published on iCarve, but it's essentially the whole paper reads like that. But it's still a brilliant result. All right. Okay, so YOLO. How does this YOLO approach, you only look once, really work? So we start with a grid for each of your images, right? So YOLO would take some image and rescale it to a certain size, 480 by 480 pixels is, I think, the standard size you start with. And then you group your image into an S by S frame. And each of those frames, each of those little segments there, is responsible for detecting an amount, a given amount, B boxes, right? And each box essentially is just, is defined by 4 coordinates, so it's the center of the thing and the height and the width, right? And you also want some sort of ground truth. How likely is it that something is in this picture at all? And you augment this with, you have a certain class of things you maybe can predict, and so you have class confidences for what each of those things are, right? So in the middle picture here, you see all the possible bounding boxes that YOLO finds, and it takes a thresholding approach, which works like that. You define a certain threshold, it's usually 0.5, and only predictions with confidence higher than this threshold are really expressed by the algorithm. So this leaves us in this example only with a dog, a bicycle, and a car, right? And all the other bounding boxes have too low a confidence to be reported back. Yeah? But the whole thing is just one neural network pass, right? So there's no preprocessing involved of any sorts, right? And it just gives you the bounding boxes. And so YOLO was kind of the first algorithm to do this in near real time. And so what you can actually do is, you can check this out on YouTube or on this guy's homepage. There's videos of object detection in real time, and it works really well. So I think the big YOLO version can handle about 40 frames a second, which is cool, but that's on a really powerful GPU, right? If you do this on a CPU, as we would see next, it might, might get a little throttled. Okay. And a smaller version of YOLO even can handle something like 150 frames per second, which is really cool. And it is almost as accurate as the former older approaches, and much faster. So the usability for, for various use cases like surveillance, definitely real. Okay, so I'm going to show you how to do deployment of the YOLO model in about 12 lines of code. And it also will feed into a lifetime, right? So the only thing we import at the beginning is the skill library, and CD2 is OpenCV, popular image manipulation library. And essentially, we've seen this before, you start your skill server, then you define your model. So you need to download YOLO v2 first. That's a TensorFlow model. And you give it a name and an ID. And afterwards you deploy it, and you get a service, right? And the lower part here is essentially just starting the webcam and feeding stuff into it. But what you should look out for is this line here, so service.detect objects. So the cool thing is that Skill automatically knows that the model you just imported is of object detection type, so it knows SSD and YOLO models, right? So if you import such a model, you can use the detect objects method on an image, right? Which is just a numpy array, could be also fine, right? And afterwards, we have a little utility functionality which annotates your image. And that's really all you have to do, right? And then your model is live, right? So demos always go wrong, but YOLO, right? So I have prepared a YOLO demo for you. So what you see here is a skill instance running on my laptop inside Docker. I wanted to do this on GPU, but I noticed too late that I actually picked a CPU image, right? So I can't really show you the power of real-time processing with YOLO. It's a little too slow, unfortunately, but we can still try. Okay, and I started the YOLO skill script, which is like an exact copy of what I've just shown you. So it's 12 lines of code, right? So it tells me that it uses TensorFlow, it's authenticating to the skill instance, then it uploads the TensorFlow model, right? It has uploaded the model and is now deploying it, which means we have to wait for model deployment for just a bit. So it should be not more than maybe 10-15 seconds. And afterwards, the webcam should start, and then we should see bounding boxes of my face, my phone, and whatever it thinks the mic is.
The skill is running now inside a Docker machine on your laptop?
Yes, okay. Exactly. And I'm also starting the client on my laptop, so it's all on my laptop. I wish I had like a fully prepared thing, but alright. What you should see is blue bounding boxes, but I expect that it maybe takes a while to get used to. Let's see. Aha! See, cell phone, 98%.
Not a Game Boy?
It's not a Game Boy. Right. So it detects me as a person. It sees me as a person, which I like. Right. That's pretty much it. I can't really show you much more. But so one thing you should know is that the data set this model was trained on is the COCO data set, which has 80 classes. It's quite pedestrian things like, I don't know, person, banana, apple. So, yeah, such things. But it will also recognize a cup and stuff like that, a fork. Yeah. So, yeah. So, I mean, worked reasonably well, but could be much faster. You know, I mean, YOLO has a much bigger throughput, but keep in mind we're doing this in virtualization, right? And we connect over HTTP, so there's quite some overhead. If you want some more high-load stuff, you could either scale out much more and have this load balancer and skill, do it on the GPU, or have some other form of online analytical processing. For instance, if you have a really, really high load that you want to use to batch your requests, for instance, something on Spark, you can do this as well. Right? Okay, thank you. Questions? Questions?
What exactly was the serving layer in this example? Is it like also scalable in the sense of like HTTP services or?
Yes, it is. Yes, exactly. And I mean, what's kind of interesting, I didn't mention this, but Skill is also, you know, platform agnostic. So I mean, if you have a cloud-based service that you want to use, maybe you're an AWS shop or your stuff is on Azure, you can connect to those cloud APIs as well. and the front end and how you use skill, the skill Python client, won't change a bit, right? It just handles resources differently. Meaning that if your existing Spark cluster is already there and it sits somewhere, maybe it's a hybrid solution, maybe it's on-premise, maybe it's in the cloud, it will still work the same way.
Do you still use Aaron for IPC in this round robin ring
Yes.
thing? Okay, the ring thing.
The ring. Cool. I mean, it's late, so it's okay. Not to ask questions.
Do you support like importing control flow from TensorFlow graphs as well? Like if statements and while statements?
Yes.
Yes. Also from. Great.
Yeah.
Does Jumpy use also ND4J in the background, or is it a different?
Also, yes.
Okay.
I would give longer answers, but it's just a
No, it's okay. Yeah, you're doing always the obvious. No, that's good.
Okay.
Thank you.
Okay.